If you are watching this video, it's because you know something about semiconductor materials. Now, it's time for numbering the devices that are made from them. Let's take a look again to our surrounding. There are diodes and transistors everywhere. Diodes in every electronic instrument, in every mobile phone battery charger, in every display, both at home and in stadium, in the mobile phone displays, and indeed they are organic ones, even in laser pointers. Watch out! There are many transistors around you. Always you need a signal needed to be amplified, equalized, filtered, and so on. This video simply introduces a classification of these components, the basic bricks of every electronic system building. Semiconductor technology is the key for achieving the miniaturization of all these components. The primitive systems that were able to control the flux of electrons crossing a vacuum gap between two metallic plates were the vacuum tubes or thermoionic tubes, or even called electron tubes. They were the bricks of the electric and electronic systems in the first half of the 20th century. The current transistors based on semiconductors appeared in 1947. It's a long way to run from them to the current packages, where 10,000 transistors are integrated in a millimeter. In this subject, we will study the operation of these devices, and mainly we will focus on their use as amplifiers, devices that take a signal at their input and provide an amplified version of that signal at their output. As we know, there are two extrinsic semiconductor types. Let's remind the N-type. The structure is like this: silicon atoms in their covalent bonds, free electrons running along the material because any bond is available from them. So we can assume that an N-type semiconductor has got positive ions mixed in with the silicon atoms structure, and electrons, free carriers, moving through the material.
In the same way, a p-type silicon has got some positive carriers, the holes, free to move across the silicon network, and a lot of negative ions that are fixed in the network. Okay, a diode is just the junction of two pieces of semiconductor, one N-type and the other one p-type. If we add to this junction two electrodes, we can work with it. Now it will be possible to extract and insert carriers from and to the junction. They are simple metallic contacts to wire the junction to the rest of the circuit. Then a diode is a p-n junction with two electrodes. Transistors are devices with three terminals. There are several possibilities. For instance, to insert a p piece of semiconductor material between a couple of n semiconductors. Three electrodes allow the contact to each one, to each zone. Electrons could be inserted and extracted from every one of them. This is a transistor, but only one of the possible transistors to be made. The name of this transistor is a bipolar junction transistor. Bipolar? Because it uses both electrons and holes to conduct a current. Junction? Because it is a transistor based on two p-n junctions, as we can see. This is not the real way to create a transistor. One doesn't glue two or three pieces of different types of semiconductor materials together in the hope of creating the junctions. The real way is to take a silicon wafer and get it doped to obtain a, for instance, N-type wafer. Here it is. Then, using the masks, a controlled diffusion of acceptor atoms is made to get a p-type zone inserted in the N wafer. Another controlled diffusion with donor dopants allows the obtention of an N-type into the p-type zone. Then two p-n junctions are formed, and three contacts can be done on each one. Of course, exchanging p and n is also possible. We will call the transistor terminals emitter, base and collector. You can see in another video how they work. Base controls the flux of carriers crossing from emitter to collector. This is in fact the transistor effect. There is another way to make transistors, using electrical field effect to control that flux. That is used in a field effect transistor. Here you are, an in-channel transistor of the junction FET type. An N-zone is the bulk of the transistor. Here it is. And two P-types, moderating the depletion zones widths of the junction form, make a real gate to control the flux of electrons upside down. In this case, the electrical field applied in the two P terminals controls that flux upside down of the electrons. This is why this is called field effect transistor. It is in an N-type, N-channel, because the electrons are carrying the current through this N-channel from here. Of course, exchanging P and N is also possible. This is a junction FET. Another way to make a FET is using a metal oxide semiconductor structure. This is a MOSFET. In this case, for instance, a P-type bulk has got two N-type diffusions, and with a high number of carriers, then the plus mark here after the N character. A silicon oxide is grown on the transistor except in the points where the contacts to the electrodes is going to be made. Electrons can cross from source to drain, and the voltage applied to the gate can control the width of the tube formed between these two zones. Again, the transistor effect appears in that way. So, summing up, a classification of transistors is shown here. FET transistor could be MOSFET or JFET. Both can be N-channel or P-channel. N if the electrons are the carriers, or P if the holes are the carriers. Anyway, they are unipolar because there is only one type of carrier involved in the transistor. Both could be enhancement type if a channel is not built from the manufacturer, or depletion type if it is done by the manufacturer. Finally, bipolar junction transistors can be made only in two ways, using a series of zones N, then P, then N, or instead P, then N, then P. See you in another video.